So my name is Miguel Nicolelis. I'm a professor of neurobiology and biomedical engineering at Duke University, and also co-director of the Center for Neuroengineering at Duke University. Well, I'm interested in understanding how large populations of brain cells interact and how they mediate behavior. And to study these populations, we have created a paradigm called brain-machine interface, in which we link living brain tissue with machines of a variety of sorts and try to see how the brain can establish interactions with these devices, bidirectional interactions. Yeah, well, we basically develop ways to sample large populations of neurons. So today we can record close to 2,000 neurons in behaving primates, which allows us to actually extract a variety of motor commands from these electrical signals generated by these 2,000 neurons. And we route these signals in real time to a variety of devices that these animals learn to control just by thinking. And we also specialize in sending feedback information from these devices, being them robotic legs, robotic arms, or even avatars, virtual bodies, back to the brain of these animals so that they can have a feel, a sense of what they are doing when they control these devices by thinking. Well, the challenge, of course, is that you cannot instruct these animals to do anything. You have to let them discover what they have to do by trial and error. So you cannot tell, do this task or perform like this. And you cannot get a report what they feel, of course, because you cannot talk to them. So it is a little art to train these animals to do these tasks and also to measure the effects of their interactions with these brain-machine interfaces. No, I actually did. Yeah. We have published already data from 36 patients, and we're about to publish 12 more. So over the last 10 years, we have in intraoperative procedures, when patients are being operated for a neurosurgical procedure, let's say Parkinsonian patients that are receiving an implant, we actually tried for short periods of time to see how patients interact with these brain-machine interfaces. And so we could see how quick, much quicker, is to get the patients to learn to do the task. Well, the good thing is, in these 36 patients, we reproduce a lot of the results that we have in monkeys. So we know that our computational strategy works. We know that the electrodes work, at least acutely. And we actually know that the patients can handle the training paradigm, and they can achieve the same kind of results in the intraoperative procedure than we get in our animal work. Not so far. No, we haven't seen anything out of the ordinary. No. Yeah, it's going to come. I think it's going to come because the results are too promising not to. But it will take time because you need to move slowly. You know, I think you need to be sure that the benefits are worthwhile and is safe, and you're really giving patients something that is relevant, not small improvements, but significant rehabilitation improvements. So you really need to restore behaviors that are essential for these patients to justify the kind of technology that we're developing here. Well, I mean, there are several projects around the world now trying to implement clinical applications of these devices. So I think the next 10 years will be pretty full of news on the clinical arena. Well, I think the science will be done much faster. We'll have the science. Now the regulatory process will depend from country to country. And then it's very complicated, and it's not my domain. I really don't know anything about it. My expertise is on developing these ideas and testing and doing the science that we can do using brain-machine interfaces. Yeah. The other people will have to be preoccupied on taking this to clinical use. Well, I think that these two brain-machine interface can be very useful in trying to better understand fundamental principles of how the brain works. So that's what I focus. Even though I'm not a clinician, I also have a project to bring this to clinical fruition in Brazil, where we hope to use an exoskeleton, a robotic vest, to restore mobility in patients using a brain-machine interface approach. So my hopes now are in these two arenas, and also in other areas, new areas, where we develop a prototype of a prosthetic device to treat Parkinson's disease. In fact, with a Swedish collaborator from Lund, where we published this in Science 3 years ago. And we now have results in monkeys, and there are 17 cases around the world that took our idea, because it's a semi-invasive procedure. It's not a, don't need to get inside the brain as the brain stimulation.
You put it on the surface of the brain?
No, you put it on the surface of the spinal cord.
Oh, right.
That was a place that nobody expected would work for Parkinson's disease, and it worked beautifully. And there are 17 cases around the world where the technique worked. So I'm hoping that now we can take this to a larger scale clinical trial, again in Brazil and here in the US, because it seems that we have found something that will have a potential implication for semi-invasive therapy for Parkinson's. Yeah, if you talk about decades, you know, I can think a lot about different scenarios on how this technology may eventually be used in addition to rehabilitation medicine. When you talk about technology that can liberate your brain power from the physical limits of the body, you are talking about something that can change dramatically the way we interact with computers, the way we interact with environments that our body cannot penetrate. So we have a demonstration 4 years ago where a monkey at Duke University in the East Coast of the United States was controlling the walking of a robot in Japan in real time, in Kyoto. So the monkey was walking in the East Coast, and the brain activity was being transmitted to Japan, and the robot walked in Japan using the brain activity coming from there. So that shows you the power of the technology, because first of all, it was a much bigger robot than the monkey. It was on the other side of the planet, and the time was pretty fast. So you can imagine other applications that could use very tiny robots or virtual avatars. And
telemedicine.
Yeah, exactly. And you can imagine the way to interact with virtual environments, computing environments, operating systems that would be totally operated by brain activity alone. So I can envision this, but there are many technological hurdles that we'll have to surpass to be able to do it. Oh, I do the science. I can talk about some of the ethical issues, but I'm not a professional. I think society needs to know what this technology is about and the limits, and it has to regulate it like any other technology. So I think it's not very different from all sorts of other modern tools that we have created. But that debate has to be much broader than just involving people like me, because I'm developing it. You know, I mean, in the eye of the hurricane. This has to be debated by other people. Well, I'm in the middle, I think. I don't think people should be scared, because the scary scenarios are only plotted by science fiction movies or science fiction writers. They are not even close to reality or what can be done. Nobody can really intrude in your brain today. No. Nobody can hack your brain and impose to you things you have to do or memories that you have to have. This is all science fiction. On the other hand, yes, you should not overstate it or oversell what this can be done. This is just the beginning of the game. We are far removed from being able to have anybody playing the violin again, you know, after being paralyzed by a spinal cord injury. This is not real. But I actually find it that much more exciting, or I feel much more excited about the prospects of using these tools to understand better how the brain works. Because I think as an experimental tool for unlocking the big mysteries of brain function, this has proved to be very useful. And we have made the discoveries in the last decade that we probably could not have done without this approach.
Can you give some examples of that?
Oh, yeah, the simple things. For instance, the fact that people thought that 15 years ago that you would have to find the right neurons in the brain to be able to control an arm or a leg. And we just put the electrodes there randomly, didn't fish for the right cells, and yet always works. If you have enough cells, so that changed our concept of what the brain is doing or what a have a contribution rather than have very special cells that will only work when you have to make this kind of movement. So these things are changing the limits of plasticity, how adaptable the brain can be, or even the limits of the concept of our sense of self. Yeah. These studies have shown that the robotic devices or even an avatar body can be assimilated by the brain as an extension of the representation of the body of the subject. That nobody knew or nobody expected. So the stream of findings that brain-machine interface has provided to systems neurobiology is pretty big right now. And to some degree, even though the applied implications are very important in rehabilitation medicine, the basic contributions to science have been, to neuroscience, have been much bigger.
That's very interesting.
Yeah. And that's how it was born.
Yeah.
I try to repeat that every conference I go because people don't realize. When John Chapin and I published this first paper on brain-machine interfaces in '99, our idea was to use it as a tool to examine the brain. We had no intention of applying this to rehabilitation. It came later. 2 years later, we published a paper saying, well, maybe this could have implications, but our goal was to create a new paradigm to probe how the brain operates at the level of populations of cells.